All right, so the second part of 1.3 is getting into postulates. And so before I got into that, I wanted to show you a resource I think it would be very valuable for you to print out and have. And that is, we have the textbook, and I do not print that. We have the odds. I don't see any reason to print that. But then, we have the geometry formula sheet, which I talked about in the welcome video. And then we have the constructions, postulates, and theorems and corollaries. So this is the document that I think would be of great value to print out. Or at least have bookmarked, and so that way you could have that pulled up and be using that and use it as a reference. So you can see that we've got, as I scan through this, and I'll tell you what, I'm going to actually pull over. I have it opened up in a full-size document, so it's a little bit easier to see. And so when you scan through here, we can see, and I'm going to go to this way right here. See, it's not going to give me an index. Sorry about that. So we've got any kind of constructions we talked about, when we talked about it. We've got postulates that are put into place. So once a postulate is talked about, it's free to use. And so once we go through a section and we've looked at this idea, then we know that those postulates can be used. So we're in section 1.3. So we'll be looking at these postulates here in 1.3, and then move on to 1.4 and so forth. And then you come down and you've got theorems and corollaries, which we'll get into later on. But once again, you can see that if you had this reference tool kind of there in front of you, it's 7 pages long. To me, it'd be very valuable. You could just look at it and scan through. If you have 2 computer screens, we could have this up on one screen and have your other screen where you're working, then I think that would be sufficient. Also, there'd be no need to print it. Or maybe you just print the pages of the chapters that we're going to work on. So for example, we only do chapters 1, 2, 3, 4, 5, 6. So there's not going to be any reason to print chapters 7 and 8 because we're not going to get to those. And so, but they're still there. They're still great references and so forth. So that's just a tool or reference that you might be interested in having it at laying on your desk when you're doing your homework to be able to be okay, well, what could I use in this particular problem? And that'll start to make more sense as we move along further in the course. All right. So with that said, I'm going to hit pause just for 1 second. So initial postulate, or initial postulates that we're going to take a look at when we jump in is that recall that a postulate is a statement that is assumed to be true. So we already know, this has already been proved, so we can just use it. So through just 2 distinct points, there's exactly 1 point, or 1 line, excuse me. And so this would be a situation where we might use this in a problem where we need to define that a certain line passes through 2 points, and so we can move forward with that. And we'll see that, like I said, as we move forward further into the course. Of course, postulate 1 also implies there's a unique line segment determined. So since on this one we have a line, then we can also then determine or imply that we have a line segment. All right, so here's some examples. In figure 133, how many distinct lines can be drawn through point A? So in point A, that would be infinite because when you think about it, we could draw any combination of lines. So if we're going through point A, we could draw a line like this. Sorry, I didn't put arrows on there. We could draw a line like this, and we could just keep going for days drawing lines. And that's why we call that an infinite or countless number of lines that can be drawn for A. For B, both points A and B are at the same time. So let's go ahead and clear this. So both points A and B at the same time. So if I draw a line through points A and B, there's only one way to do that, and there it is. I know it's not perfect, but there's only one way. Doesn't matter whether I come from the top down through A and then through B, or up from B and up through A. All right, and then last but not least, a line that contains all the points A, B, and C at the same time. So in Euclidean geometry, which is what we're working in, which I really hadn't said that to you before, in Euclidean geometry, we can only draw straight lines. So, and I apologize, I don't know off the top of my head what the other spaces that we could work in, but in the geometry we're working in, we can only draw that straight line. So when we do that, there's no way for us to draw a line like that because that's not a straight line by definitions inside of, or our assumed definitions inside of Euclidean geometry. I'm just gonna, there we go, moved over for me. All right, so some more initial postulates, and this is just kind of like running through some things. Some of the assignments you might be talking about is like the symbol for a line segment. We talked about before is AB. Those lack of arrows on top signify that it stops at A or starts at A and goes to B and stops at B. The emission of the bar, it means length. So if we don't have the bar in there, but we have italicized AB, that means the length of it. And a ruler can be used to measure the length. The length can be represented as BA or AB. However, AB must be positive because the idea is that if it's a measurement, it's got to be positive. It can't be negative. So we got a little table there. Postulate 2, the measure of any line segment is a unique positive number. So once again, why is it positive? Because it's a measurement. It's a length. Length cannot mean negative. Negative is just a quantity measuring difference between two numbers. So we wish to call attention to the term unique. There's a general notion of uniqueness. Unique, one and only one. There's exactly one and no more than one. So the ruler postulate implies the following. There exists a number measure for each line segment. So there exists a number measurement for each line segment. So the ruler postulate is that if I have a line segment, I can measure that and get a distance for it. Only one measure is permissible, because if you measure that, if you're measuring accurately, there's only going to be one. Okay, so characters 1 and 2 are necessary. A more accurate claim that is commonly heard is the shortest distance between 2 points is called a straight line. So the definition is the distance between 2 points A and B is the length of the line segment AB that joins the 2 points. That leads us to postulate 3. If X is a point of AB where we have AXB, where X is on line AB between A and B, then AX plus XB is equal to AB. So that's just kind of this idea of a segment addition, that we can break this up. Let's see if I have a picture on the next slide. Nope. So that's just saying that basically, like if I had a line segment, let's call this A, and we'll call this B, and we take this guy and we draw the line across there. And then we say, okay, well, then we come along and let's put an X right there. Then line segment AX, or the measure of AX, and the measure of XB would be equal to, so we add those together, that's naturally equal to the measurement of AB. So it's so intuitive. You're like, oh, why do we need to talk about that? But it's because we need these rules, these definitions, these postulates to make sure that we're applying things correctly. All right, so continuing those initial postulates, so just kind of working through some of them, talking about it. We have congruence. So congruence is going to be the equal sign with a little tilde on top. And so congruent line segments are 2 line segments that have the same length. And geometric figures that can be made to coincide or fit perfectly one on top of each other are said to be congruent. The symbol of congruence is a combination of a tilde with an equal sign, and it means that the corresponding parts of the figures have the same measure. So corresponding parts of the same figures have the same measure. So let's see what that applies. So for example, we take a look at this. Line segment AB is congruent to line segment BCD. Notice we're not using an equal sign because we're not talking about measure. We're talking about this idea that the lines are they have this congruence, and so that means the corresponding parts have the same measure. So it's a little bit slightly different deal. And then we continue on. It says meaning that, but AB is not congruent to EF, meaning that the AB and EF are not congruent. It does appear that CD is congruent to EF. Oh, I'm sorry, does it appear? And of course not, because you can clearly see that if we did the measurement with a ruler, CD is only a portion. So the idea of midpoint comes up next, and that with a definition that we can use with these postulates. And so a midpoint is a line segment, is the point that separates a line segment into 2 congruent parts. So in figure 1.36, what we see is that we have A, M, and B, and they're collinear. And what we see, and one symbol that we can use here to mark as congruence, is that we can say that line segment AM is congruent to line segment MB, then M, if they are, then M is known as the midpoint. So if M is in, if those two line segments are congruent, then we know that M is the endpoint. These little bars right here signify that those two line segments are congruent inside of line segment AB. So equivalently, M is the midpoint at AB. So remember, with a good definition, we can go forwards and backwards. And so they go ahead and go backwards with that. And then also we can say that AM is, then CD is known as the bisector. So line segment CD cuts AB in half. It's the bisector. So these are just all terminologies. Now with that, then we have these different combinations or relationships. So we can say that the measure of AM is equal to MB. So remember, AM is equal to MB, measure. We can say the measure of MB. So MB is right here, is equal to half of AB. We can say that AB takes two of these. So it would take two of those, because if we put those together, it would be two of them, and so forth and so on. So we have these different relationships that we can then start measuring at that point. Array, the difference between array, a line segment, and a line is that array is going to start at one of the vertices and continue on through the other one. So it has an endpoint that continues on through the other point. So it could be array A, B, or it could be, oops, sorry about that. It could be array A, B, it could be array B, A. Opposite rays. So if we have a point B that is collinear with A, B, C in the middle there, then we can say that we have ray BA. Sorry about that. We can say that we have ray BA, which would be opposite ray BC. Intersections. So intersection is pretty straightforward. That's where we have two lines that intersect at one point. And so if two lines intersect, they intersect at a point. And we also can call that they coincide. So those lines coincide at that particular point. And so we've got some examples there that we can take a look at. Parallel lines. So going into this, it seems very straightforward, but parallel lines are lines that lie in the same plane. So like we know, like the most simplified situation is that if I have a plane, and so what I want you to think about here is that I'm going to call V a plane. So inside of in plane V, I have a line that runs like here, and I have a line that runs right there, and we'll call this line L and line M. Line L and line M are parallel because they're in the same plane. If two lines are not in the same plane, so like if I had line L here, and I had line M over here, I mean, obviously they don't look parallel, but we can't say they're parallel because they're not in the same plane. And so it's like there's a possibility they could intersect or whatever it is. Whereas with planes, a plane is two-dimensional. It has an infinite length and an infinite width, but no thickness. So what I need you to envision here is that, let's look at R and S, or T and V, doesn't matter. What I need you to envision is that even though we call R a plane, that plane, this side right here actually goes on forever. So like this side right here goes on forever. And this side right here goes on forever this way. And this side right here goes on forever that way, and so forth to this side. It doesn't go up or down, so it just goes straight out. So just kind of like imagine like a piece of paper, and you just wanted to expand that piece of paper. It's just laying there. So that's why we call it that doesn't have any thickness. Even though a piece of paper has thickness, a plane to naked eye doesn't have thickness necessarily. We just got a couple more things. We can talk about the idea of non-collinear. So two distances, two distinct points may determine a line. Likewise, three non-collinear points determine a plane. So what they're saying here is that I can say that if I have, if I have point C, point D, and point E, they're not linear, they're not collinear, but they can determine a plane, because I can say the plane's made up of points C, D, and E. Just as collinear points lie on the same line, coplanar points lie in the same plane. So in this case right here, we have this plane right here that we call, let's call it plane F. And in plane F, we have coplanar points because they lie in the same plane. All right. Whereas A, B, C, D, E are not coplanar because A is out here. And what we got to think about that is that's like basically like drawing a line straight up out of the plane. So that's not coplanar. See, points shown in figures are generally assumed to be coplanar. So like if I draw an angle like we see here in figure 143A and 143B, if I draw angles like this, then it's assumed that those are coplanar. So it's kind of just a little vocabulary piece. All right, and then we're kind of breaking back through. So we're just going through these postulates. So we know that postulate 5 says through 3 non-collinear points, there's exactly one plane. So non-collinear. So C, E, and D are non-collinear, or B, C, E are non-collinear, any combination. So they're not on the same line, so therefore they can make up a plane. And that's, we can see why a 3-legged table sits evenly, but a 4-legged table would wobble if the legs were unequal in length. Just kind of just we'll chew on that for a minute and kind of see what that says to you. Space. Space is a set of all possible points in a 3-dimensional, and it is 3-dimensional, having qualities of length, width, and depth. When 2 planes intersect in space, they intersect to form a line. So in this case right here, I have plane R and plane S. When they intersect, they're going to form a line. So we have a postulate that comes off of that. All right, we can have parallel, the parallel vertical planes. Think about those opposite sides of the classroom. We can have horizontal vertical planes. That's M and N. Think of those as the ceiling and the floor. That leads us to postulate 7. Then we got theorem 1.31, which we're interested in for the first time. The midpoint of a line segment is unique. And so we can then apply that. And that wraps up our different postulates that we're going to start off with for section 1.3. These videos definitely get